All right. Thank you. All right. So, a couple of things. One was we're obviously working on the hydrogen atom, and we spent a lot of time on it. In particular, we solved the radial part in a lot of detail, and so it felt to me a bit, I don't know, like why didn't we solve the angular part in as much detail? And one reason is because it's a lot of the same procedure, although the details are different. Um, I got interested in it, and so I did spend some time reading and solving that problem. So I posted those notes on the course website. If anybody's interested, they can look at it. But it's not something I'm gonna test you on or ask you to reproduce or anything. It's just if you're curious about it, you can read them. Yes.
For the radial part, we would like on tests and stuff, the questions would be asked to like solve for the radial part.
No, I'm not going to expect you to memorize all those variable transformations and anything, but the process of how we got there would be something I could ask.
So like process as in we wouldn't have to memorize those like variable transformations, but we would have to know, oh, this sum like the summation way to solve it and all of those
Sure.
series, right?
Yeah, yeah, that's fair enough to say. Yeah. Yeah. So those notes are available on the course website. We have we have 4 classes left, including today's. And so what we're going to do is we're going to finish off our discussion of orbital angular momentum. We'll probably finish that today. And then we're going to talk about the electron spin. There's a section in this chapter that is addition of angular momentum. It's unclear whether or not we'll get there, but I will let you know exactly where the cutoff is for material that could appear on the final exam. Also, I will recommend another set of problems based off of the hydrogen atom and angular momentum and spin that we're talking about, but I'm not going to collect another new assignment. Those will just be recommended problems from the textbook. If you want to work ahead, they're, like always, they're just going to be the problems that have 1 star beside them. Those are Griffith's way of saying these are important ones that everybody should do. All right. So what we were talking about was angular momentum, specifically the orbital angular momentum of the electron motion around the proton. And we had been working out, I know it was abstract, but we were working out a lot of the angular momentum algebra in terms of commutator relations. And so I've summarized a bunch of the important results. The kind of the path we're following is sort of analogous to the raising and lowering operators that we saw for the harmonic oscillator. We made a raising and lowering operator for the orbital angular momentum, and what it did is it increased the eigenvalue of the z component of the angular momentum by 1. So every time we act with L plus on, say, an eigenfunction of the z component of the angular momentum, it increases that state by h bar. So if we were in a state of like, I don't know, 3h bar, then we act on with the raising operator, we get the 4h bar, then 5h bar, then 6, and so on. But that would lead to a bit of a problem because eventually we would act so many times with the raising operator that we would get to a position where, or I don't know, a case where if we raise the z component of the orbital angular momentum anymore, it would be above the total angular momentum, and that can't possibly happen. So there has to be some state ft for top of the ladder, where if we act with the raising operator 1 more time, we're going to get a 0. Likewise, I could act with the lowering operator over and over and over and over again. I could get into a state of negative z component of angular momentum. But once I make it too negative, it's going to become more negative than the length of the total angular momentum, and we can't have that. And we're going to have an L minus acting on an F bottom that would have to be 0. So anyways, where we got to at the end of last time was that we showed that if we acted with the L squared operator on our F top state, we would get this eigenvalue, j times j plus 1 times h bar squared. And if we acted on that same F top state with the Z, LZ operator, we get JH bar times F top. So what we're going to do is we're going to do the opposite today. It's kind of nice because we'll review how we got this, but we're going to do it for the bottom state. Okay, so as a continuation of last time's notes, we would say likewise, in a state F bottom, so this is now bottom, with a minimum LZ, we must have, okay, so LZ acting on F bottom is equal to, well, this is a new eigenstate, so it's going to have a new eigenvalue. We used J times H bar times F top for the top state. I'm going to use J prime times H bar times F bottom. Remember, the reason we factored out an H bar is because we came to the realization that H bar has units of joules, seconds. That's exactly the units of angular momentum. So if we factor out an H bar, then this J and the J prime, they're just unitless. So that's kind of nice. Yeah.
Have we solved for what J is yet? Or is it just...
We're going to do it. We're about to do it. Yeah. Okay, so L minus acting on the bottom state would have to be 0 because we are presumed in the lowest possible Z component of the angular momentum. We can't go any lower than that. So to go further, what we're going to do is we're going to go back to this equation star. I'll put it at the top here. In order to work out this, what we ended up doing is we took the bottom sign. What we're going to do now is we're going to take the top sign. So at the top of the screen, we'll take L plus, L minus, plus LZ squared minus H bar LZ. Why are we taking the top sign? Because what we're going to do is we're going to act on F bottom with that star, and that first term will begin with L minus times F bottom. And that, by definition, has to be 0. So we're going to get rid of that first term. Okay, so we're going to take the top sign of star. And let's go. So the top sign of star would give us L plus equal, sorry, L squared is L plus, L minus, plus LZ squared minus H bar LZ. Okay, so such that L squared acting on the bottom state is going to be some eigenvalue, and then we'll get F bottom back. And so we're going to have L plus, L minus, plus LZ squared minus H bar LZ F bottom. And let's see, F bottom, act on it with L minus, that's a 0. F bottom, act on it with LZ, we're going to get J prime H bar. But then we have to act on it again. So we're going to get J prime H bar squared. So we have a J prime squared, H bar squared, minus H bar. We act with LZ again, we'll get a J prime H bar. And let's see, we'll have our eigenstate returned back again. And so let's see, H bar squared, we can factor out 1 J prime, and that will tell us what our lambda eigenvalue is. So therefore, lambda is equal to J prime minus 1, H bar squared. And this I'll call equation B, because we're going to pair it with our equation A. And where did it go? Where's equation A? I can't fit it on there. Oh, equation A I didn't write down. This one was equation A right here. That was A from our notes last time. And so let's just take a look at A. J times J plus 1, whereas in B, we have J prime times J prime minus 1. Now, L squared acting on F bottom and F top, the distinction between F bottom and F top is just the value of the Z component of the angular momentum. It's not the total angular momentum. The total angular momentum is the same. All we've done is change the Z component, but overall, the length of the total angular momentum hasn't changed. So these expressions for lambda in equations A and B have to be equal to each other. And so let's see what that implies. So comparing A and B is going to require. Okay, so I don't care about the factor of h bar squared. They both have that h bar squared, but we're going to have a j times j plus 1 is equal to j prime times j prime minus 1. So if you think about it, there's two possible solutions to this relating j and j prime. One possibility, so possible solution is j prime is equal to j plus 1. Why does that work? Suppose I put in j plus 1 for j prime on the right. So I'm going to get a j plus 1, and then I'll get a j plus 1 minus 1, which is j. And so I get j times j plus 1, which is exactly what we have on the left. So that makes sense, except for j prime was supposed to be telling us the total z component, I shouldn't say total, the z component of the angular momentum when we're in the bottom state. So I can't put j prime as j plus 1 because j was the total sorry, I can't say total, the z component of the angular momentum in the top state. So the top and bottom, they should have the same magnitude of z component of the angular momentum. I can't increase the bottom one because then it's going to have more than the total angular momentum of j times j plus 1 all square root. Okay, but this can't work because then the lowest state at the bottom of our ladder, FB, has higher LZ than the top state, FT. So we got to look for another possibility. So another possible solution is that, well, what if I put in j prime is equal to minus j? So I'm going to put in minus j here, and then I'm going to put in a minus j here. But then if I propagate in this minus sign, I get minus times minus j is plus j plus 1. And so that would make the left and right sides equal. Okay, so let's just try that. So j prime minus 1 would go to, let's see, minus j times minus j minus 1, which is equal to j plus 1. And so that works out nice. All right. So therefore, the max LZ eigenvalue is, well, LZ acting on F top is going to be J H bar F top. So that we had already written down. But But now what we've discovered is that the minimum LZ eigenvalue is LZ acting on F bottom is J prime H bar times F bottom, but J prime is equal to minus J. So it's minus J H bar F bottom. Now this is quite nice, as a matter of fact, because if I was to now take this bottom state and act with L plus over and over and over again, I'm going to keep increasing this eigenvalue by H bar. So we'll go from minus J H bar to minus J plus 1 times H bar, minus J plus 2 H bar. And I'll just keep going and going and going. I'll do it n times, and that'll take me to J times, well, I'll get to J minus 1 times H bar, and then I act one more time, I get to J times H bar. It'll also raise the state to F top. And if I try to do it again, L plus acting on F top will give me a 0. Okay, so acting on F bottom with L plus repeatedly, let's say n times, will increase the LZ eigenvalue by H bar. So that is JH bar will go to J plus 1. Well, okay, I should be a little bit careful. Let's say minus JH bar would go to minus J plus 1 times H bar, and then that would just keep going. So you do that over and over and over again. Each time until we reach F top, at which point LZ F top will be JH bar F top, and L plus times F top will be 0. So no more raising is allowed. So let's go ahead and see what are the actual values of J. What is allowed for J? Okay, well, what we could say already is the LZ eigenvalues span. Okay, so minus J H bar, and then it goes to minus J plus 1 H bar. And then it keeps going. We'll get to J minus 1 times H bar, and then finally we'll reach J H bar. Okay, so this is n times. We're going to act with this L plus, and so we have minus J plus n equals J. Each time we increase J plus times 1 because we have we increase the eigenvalue by H bar, so that's like adding plus 1 to the J. So plus 1 plus 1 plus 1 plus 1 plus 1 n times gives us a plus n. Well, that's kind of nice because then I can bring this J over here. I have 2J is equal to n, or J is equal to n by 2. All right. So in other words, n is clearly an integer. There's a couple possibilities. One is, suppose n is even, then we divide by 2, we just get some integer. So if n is even, then j is integer. So in other words, j must be either integer for n even, or half integer if n is odd. Now that's a little surprising because we may have been anticipating that if we're going to connect our little L from solving the angular part of the hydrogen's wave function, we discovered that little l had to be integer. That was all that was allowed. That's not good. So if that's all that's allowed, then it seems like there's kind of half of our possible eigenvalues are not valid solutions. And that's absolutely true for orbital angular momentum. We will show that the eigenfunctions, so far we've just been writing like f top and f bottom and just a generic f. We're going to show that those f's are actually exactly the spherical harmonics. And therefore, the eigenvalues, this j times j plus 1 is going to be exactly L times L plus 1 for the orbital angular momentum. But there is the possibility from this analysis of the algebra of angular momentum that we could have half-integer solutions, and that is going to be the topic of spin after we complete this. Yeah.
Oh, wasn't M the one that was related to the Z hook to angular momentum?
Yes, but J is also this lambda here was the eigenvalue of L squared. And that's where the little L is going to be associated with that. Yeah. Okay. So let's just make a note that this is the half integer solutions are surprising because we were anticipating j integer to correspond to L integer from the solution to it's from the solution of it was really the theta part of the wave function. We will investigate the half integer solutions when we discuss the electron spin. But for now, what I want to do is I want to finish off our orbital angular momentum discussion. Okay, so L squared acting on F, J, M. Okay, I think I've been using MJ, I think, so I'll stick with that. All right, so we've now shown that the eigenvalue of L squared is j times j plus 1. There's a factor of h bar squared, and then we get our eigenfunction back again. And now we've said Lz, acting, it has a common eigenfunction with L squared, and its eigenvalue was the m part. When we were doing f top and f bottom, what we were doing is we were finding the extreme values of m. And those extreme values of m are plus and minus j. But we can have all of the integer steps between them. So in general, what's possible for any kind of angular momentum is j can be integer or half integer. For the orbital angular momentum, it'll only be the integer values that are important. And then mj spans minus j to plus j in steps of 1. So that means for a given value of j, there are how many? There are 2j plus 1 values of mj. So it's 2j because you have the positive and negative And then the plus 1 is because you could have 0 as well. All right. So that's our summary of the eigenvalues. It's kind of when you step back and think about it, it's kind of neat that we were able to deduce these eigenvalues without ever writing down the eigenfunctions. But that's what we're going to try to do now. So next, we will show that these eigenfunctions, fj, mj, will turn out to be the spherical harmonics. So yj, mj, theta phi. The quantized J and mj will be associated with orbital angular momentum, and J will be L and will only accept integer values, and mj will just be the m's that we had found. So L associated with the total orbital angular momentum, capital L squared, and m associated with the z component. All right, good. So actually, this next section showing that the eigenfunctions are the spherical harmonics, I find is less abstract than finding the actual eigenvalues. So let's give it a go. 4.3.2. So these are the eigenfunctions of L squared and Lz. Okay. So in general, L is going to be minus IH bar R cross this gradient operator. The reason we could write it this way is because angular momentum is R cross P, but in quantum mechanics, P is minus IH bar d by dx, for example, for Px. And so here's our minus IH bar, and then this is just a vector of I hat d by dx plus j hat d by dy plus k hat d by dz. And so that's a vector representation of the angular momentum quantum operator, where we have used Fp is equal to minus I h bar times the gradient. Okay, now for the hydrogen atom, we are working in spherical coordinates. The reason we used spherical coordinates was because of the symmetry of the potential. The Coulomb potential between the proton and the electron depends only on the radial distance between the two. And then it has symmetry in the angular coordinates. And so that's why our spherical coordinates were so convenient. So in spherical coordinates, let's see, this gradient operator is a little messy, but it's not too bad. So there's a 1 over r sine theta d by d phi. Okay. Now, to write down the angular momentum, I have to take the cross product with r. Okay, so using, let's see, vector r is its length times its unit vector. What's r hat cross with itself? What's the cross product of any parallel vectors? 0. Okay, so that's going to be 0. That first term's going to vanish. And so look, you know radial derivatives. So theta hat and r hat are perpendicular. So their cross product is going to give another perpendicular vector, a unit vector. And so that the only thing that could be perpendicular to both r hat and theta hat is phi hat. And so all we have to worry about is it plus or minus phi hat. So it turns out that, okay, we already saw that this one's going to be 0. R hat cross with theta hat turns out to be plus phi hat. And then r hat cross with phi hat is minus theta hat. Okay, so that means our angular momentum operator, written as a vector, it has this factor of minus IH bar. And let's see, there it is. Okay, so we'll get theta hat cross, r hat cross theta hat was a phi hat. So we'll get a phi hat. Now, this 1 over r is going to cancel with this r. And so not only is there no radial component, no radial derivative, there's going to be no r dependence whatsoever. We're going to get a d by d theta. And then for phi hat, the r cross phi hat is going to cancel this r. And then r hat cross phi hat is minus theta hat. So we'll get a minus theta hat. And then we'll have a 1 over sine theta. And then we still have our d by d phi. All right. Good. Now, at this point, having evaluated that cross product, I'm going to now go back to Cartesian coordinates. Why are we going to do that? Because we've already seen that the z component of the angular momentum is of central importance. And so I want to recover that z component. We've also already seen that the x and y components combine to give our raising and lowering operators, and maybe that will be useful. We'll find out. So in terms of Cartesian coordinates, let's see, theta hat is cos theta cos phi I hat plus cos theta sine phi j hat minus sine theta k hat. You might remember at the beginning of our last class, I had a picture of the spherical coordinates on a Cartesian coordinate set of axes. And so this relation is exactly obtained from the geometry that was written down in that little picture. So phi hat is minus sine phi I hat plus cos phi j hat. Okay, so all I'm going to do is stick this thing in for phi hat and this thing for theta hat. And let's see what happens. So therefore, L is minus IH bar. Okay, so we'll start with the phi hat. That's the one that's a little nicer. Cos phi j hat. And then it was what? A d by d theta. Okay. Then we had a minus, and then theta hat. Okay. So theta hat is, let's see, cos theta cos phi cos theta sine phi minus sine theta k hat. And let's see, there's a 1 over sine theta, and there was a d by d phi. Okay, good. And I've got to close my bracket. All right. So you can kind of see, I guess, these sine thetas are going to cancel, but then these other terms are going to have cos theta over sine theta, cos theta over sine theta. And so we'll probably end up with like this inverse tan or cotan function. All right. So what I want to do is I want to combine terms that are going to be in the same direction. Okay, and so that's what we have. All right. So I want to pick off the X, Y, and Z components. So we'll start with X. We have minus IH bar. Let's see, minus sine phi. Okay. And then we have, there's the cos divided by sine. So we're going to get cotan theta cos phi. All right, so I have to write down first my d by d theta. Let's not forget that. Then minus cotangent of theta cos of phi. And then we have a d by d phi. Okay, yes, that looks right. All right, Ly. Okay, minus IH bar. And let's see, we have a cos phi d by d theta. Cos phi d by d theta. And then we have a minus cotan again, but times sine of phi. And then we have d by d phi. So cotan theta, sine of phi, d by d phi. And the lovely one is Lz. It's minus IH bar, d by d phi. Why is that lovely? It's because, if you remember, when we solved the phi part of hydrogen's wave function, all it was e to the im phi. And that phi derivative's going to bring down a factor of im. When you bring down that I, you get minus I squared, that's plus 1. And then you get m times h bar. That's exactly the eigenvalues that we just calculated. And so the z component of the angular momentum, orbital angular momentum, depends only on the phi coordinate, and that was the simplest one that we solved when we were doing this hydrogen function, hydrogen wave function. Okay, good. So we've got that. All right, so now what's going to happen is we're going to try to write down the raising and lowering operators. Okay, so L plus minus is Lx plus minus ILY. All right, so this is really the only part where there's a bit of writing and algebra to do, but it's not hard. It's just full of i's and negative signs. And so there's a very high probability that I will make a sign mistake. But let's see how that goes. This is not L plus, this is LX. LX. Okay, good. Okay, so minus IH bar. And then Lx, we just got to write that stuff down. So it is minus sine phi. Now let's see. What did I do? Okay, I see what I did. What I'm going to try to do is I'm going to try to write the theta derivatives together. So the minus sine phi is from the x component. From the y component, we're going to get a cos phi, but I have to multiply it by plus or minus I. So plus or minus I cos phi is I think what we have. Plus or minus I cos phi. And then all of that stuff multiplies the theta derivative. And so I want to do the same thing for the phi derivative. So I'm going to leave a bit of space here. So I'm going to do minus. So cotangent cos phi. Okay. So I'm going to put the cos phi here, and I'll put the cotangent here, and then we have a d by d phi. Okay, so that's the LX one. And then we have to do the LY. I've already pulled out the minus sign here. So we've taken care of that minus sign. I've already pulled out the cotangent and the d by d phi. So we dealt with that. And so what do we have left? We have a plus or minus I times sine phi. Okay, uh, plus or minus I sine phi. Okay, so I think so far we're okay with signs. We shall find out. Um, one of these is easy to deal with. What's this thing above the red squiggly line? Yeah,
Use the I5.
it's e to the I phi, almost exactly right. What am I missing? Plus or minus. That's right. Okay. So I want to do the same thing for this one. We just have to be careful with the signs and the I's and stuff like that. So that first one has a minus sine phi. I'm just going to write it exactly as it is there, plus or minus I cos phi. Okay, I'm going to factor out the I. So I factor out the I. We're going to get a plus minus cos phi. I'll have a 1 over I sine of phi. Okay, so what are the chances somebody's got a lightning charger cable here? If you do, let me know. Otherwise, I'll be running to my office probably once this dies. Okay, good. So this minus 1 over I, we could multiply it by I over I. And then I'd get I squared in the denominator. That's minus 1. Just going to cancel that minus sign. So this is just I in the numerator, like so. All right. So this is equal to I. And then I'm going to put plus or minus cos phi first. And then we have plus I sine phi. Okay, now we're almost where we need to be. What I'm going to do is I'm going to factor out the plus minus. Plus minus I cos phi plus minus I sine phi. We can check. This one, the second term should always be plus. If I take the plus sign, the top one, I get plus times plus, positive. That's good. If I take the bottom sign, I get minus times minus, positive. That's good. Okay. And so this is exactly like before. This is plus or minus I e to the plus or minus I phi. Good. So this one is plus or minus e to the plus or minus I phi. And so you can see that's going to simplify our raising and lowering operators quite a bit. So what we're left with is the following. So therefore, L plus or minus. What do we have? It's minus h bar e to the plus minus I phi. Let's see, can I get all of this stuff on here? Yes, sort of. Now, what did I do with, sorry, I know what I did. I forgot my I. We said there was going to be an I in front of this one. So what I'm going to do is I'm going to have the minus h bar, and then I'm going to bring the I inside. If I bring the I inside, this this plus minus I becomes plus minus I squared, which just becomes a minus plus. So inside of our brackets, we're going to have a minus plus, and then it's a d by d theta, because I've already taken out that exponential. Okay, and then what's the next term? We're going to get a minus I because I brought the I inside. So minus I This we've already taken out. And now we have cotan times d by d phi. So cotangent of theta d by d phi, like so. All right, this is pretty close to what we wanted. I'm going to bring the minus sign inside. H bar e to the plus minus I phi. So I bring in the minus sign, I can come back to a plus minus d by d theta. Then we get a plus I cotangent theta d by d phi. All right, last step. L plus minus is equal to, what I'm going to do now is factor out the plus minus. Probably there is a more efficient way to do this, but this is the way I could get it done without making a bunch of sign errors, presumably. So I factor out the plus minus, the plus becomes a plus minus I cotan, cotan theta, d by d phi. All right. So what I'm going to do is I'm going to leave a little exercise for you in the recommended problems that I'll suggest, and I'll get those out this week sometime. They'll go on the course website. The problem that one of the problems I'll recommend is 4.24. You will show. It's nothing really that technical. What we're going to want is the product of L plus and L minus. And so if you work out the product of L plus and L minus, you just take these two things. You take the top sign for the plus and the bottom sign for the minus, you multiply them together. What's going to happen? Well, the theta derivative is going to act on this cotangent of theta. So you have to evaluate that derivative. The phi derivative will act on the e to the plus minus I phi. So you have to evaluate that derivative. But that's really all you're doing. This comes out to be minus h bar squared d2 d theta 2 plus cotangent of theta d by d theta plus cotangent squared theta d2 d phi 2 plus I d by d phi. Okay, so that's the result. Why did I want that? Well, let me just go back and show you why I wanted that. It's way back here. It's because I can write L squared in terms of L plus and L minus and some LZ operators. And so that's what we want to do. So that was equation star. So where did we go? Okay, that's where we were. So, and using equation star, which was really, we derived it last week, but worked with it today. Our L squared operator becomes minus h bar squared. So it's 1 over sine theta d by d theta d by d theta plus 1 over sine squared theta d2 d phi 2. So this is getting this result is also part of 424. But what you would do is you would use the L plus L minus here. But then you had also LZs. You had an LZ squared and you had an H bar times LZ. And for that, you would use this thing wherever you see the LZ. And then you have everything expressed in terms of derivatives with respect to either theta or phi. All right. Now, if you look at this, it might start to look kind of familiar depending on how fresh it is in your mind. But when we did separation of variables for the hydrogen atom, in particular, the Coulomb potential of the hydrogen atom, the angular part looked an awful lot like this. And we know the solution to the angular part is the spherical harmonics. So that's where we're going. Let's see, we have around 20 something minutes left. We'll see if our battery survives. Yeah, this is an old one. It's a lightning. Yeah, thanks. I have a new one, but I didn't get it to work yet. We'll see. We're gonna get close anyways. We can now find the eigenfunction of L squared with eigenvalue. You've got one? Oh, brilliant. Thank you. That's perfect. So let's see. Now, last time I did this, and I discovered that the desk wasn't plugged in. Oh, but it appears to be now. All right. Thank you very much. Don't let me forget this. All right. So L squared with eigenvalue h bar squared at j plus 1. Okay. So L squared fj mj. So we're going to act on some state, some eigenfunction of L squared. We're trying to find this f. Okay, so that's what we're trying to do. Well, L squared is just this big mess of angle derivatives. So sine theta d by d theta plus 1 over sine squared theta d2 d phi 2 acting on fjmj is equal to the eigenvalue, but we already know what we need for the eigenvalue. We just worked out that eigenvalue. fjmj. Okay. And so, in fact, we're basically done because if you go look at our separation of variables for the hydrogen atom, this was exactly the angular part. This solution we could separate further into just the theta equation and just the phi equation. The phi equation will have the eigenvalue, the eigenfunction e to the jm phi. The theta part will have as its eigenfunction those associated Legendre functions. That's the one that I just posted those supplementary notes where we walk through the entire solution. So this is exactly the angular part of the Schrodinger equation we got after separation of variables. And so in the book, this is equation 418. So this looks just like equation 418. And so we know the solution. We know the solution is f j mj is y j mj theta phi, and these are the spherical harmonics. Okay, so J determines the total angular momentum. L squared yj is equal to h bar squared j plus 1. That's yj. Now, when we solved the spherical harmonics, we said the eigenvalues, we wrote them as L, they have to be integer. So here, j must be integer. And in fact, what we'll do for orbital angular momentum, j goes to L, and L is integer. Okay, good. So what about LZ? Well, likewise, since L squared and LZ commute, their commutator is 0. We have, or they, let's say they have common eigenfunctions. Okay, so that means LZ acting on our spherical harmonics is going to be, well, we just worked out the LZ operator. It was minus IH bar d by d5. We kind of actually did what I'm about to write down. We did this in our head. It's going to act on the spherical harmonics. But the spherical harmonics we could separate into the theta and phi parts. So the theta part just passes right through the phi derivative. And then we have our phi derivative acting on the phi part. But the phi part is e to the j mj. Sorry, e to the, I should say I mj. Okay. But then when we do the derivative and I mj comes down, minus I squared is just plus 1. And so we get mj Apple Pencil battery is low. Come on. mj h bar. Let's see. And then we'll have our theta and our phi. And that's just mjh bar times the spherical harmonics. And so lo and behold, we have our eigenvalue equation. Operator acting on an eigenfunction returns an eigenvalue and the same eigenfunction back. Okay, good. So this quantization of the z component of the angular momentum is determined by the symmetry of rotating around that z-axis. Going around the z-axis once meant that the, where did it go? Sorry. This thing had to be single valued. So if I forgot, there should be a phi in here, right? So if I take phi and then change that to phi plus 2 pi, it has to be single valued. And that's what led to quantization of the z component of the angular momentum. So therefore, we've kind of wrapped up a lot of the standard analysis of the hydrogen atom. We've calculated the entire spatial wave function. It involved a radial part, and it involved an angular part. And so this is a simultaneous eigenfunction of all of the Hamiltonian, of the L squared operator, and of the LZ operator. And so when we talk about the stationary states of the hydrogen atom, that involves quantized energy, quantized total angular momentum, and quantized Z component of the angular momentum. If you make a measurement of your electron in your hydrogen atom, you will collapse the wave function into a state of definite energy, definite orbital angular momentum, and definite Z component of that orbital angular momentum. And because they're stationary states, after that measurement, the system will not evolve away from that state. It will stay in that state. Okay, so let's just summarize. If I act with my Hamiltonian, I get En. And that En was minus 13.6 electron volts divided by n squared. That's the binding energy of the electron, because if we go to an energy that's positive, we no longer have a bound state, we have scattering states. L squared is going to give us h bar squared L plus 1, psi and Lm, and Lz is going to give us h bar m psi and Lm. All right, good. So we have 10 or so minutes left. And so that's actually a really nice place where we can just do a soft introduction to spin, and then we can start grinding through the details next time. All right. So when solving the hydrogen atom, we specified that L was integer. However, when finding the eigenvalues of L squared, we discovered that J could be integer or half integer. So we examine this, let's say, oddity next. Okay, so the way we're going to begin is I just want to have like a classical analog of what we're going to mean when we talk about this property called spin. And so the classical analog I want to imagine is just the Earth going around the sun. So let's consider the Earth orbiting the sun. Okay, so this picture is not going to be to scale, but there's the sun. Maybe I'll give myself a little more room. And what I want to do is I want to draw an orbit around the sun. So there it is. Get that locked in place. Okay, and so this is going to be the trajectory of the Earth as it goes around the sun. And so my Earth is over here. Oh, whoops. No, 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 no. I wanted this one. All right. Oh, sorry, I'll get it. I want my fill to be white. All right, good. So here's Earth. And the distance from the center of the sun to the center of the Earth is some radius r, and our Earth is moving with some kind of tangential velocity at v. Okay, so the what we've been talking about so far is orbital angular momentum, and the Earth definitely has orbital angular momentum around the sun. It would just be given by the cross product between r and the momentum, or m times v, of the Earth. So the Earth has orbital angular momentum. L is r cross the mass of the Earth times its tangential velocity. Okay, but that's not the only angular momentum that the Earth has. The Earth is also spinning about its axis that approximately goes through the two poles. And so we could imagine the Earth as we can chop it up into these little chunks. And each little chunk is like a point mass going around an axis, and it has its own orbital angular momentum around Earth's axis. And we sum up those contributions from all the little point masses that make up the total Earth, and that is a angular momentum associated with the spin of the Earth. And we're going to call that spin angular momentum. So, however, the Earth has another contribution to its total orbital, its total angular momentum due to its spin slash rotation about its own axis. So we could try to draw a picture of what that looks like. All right, let's give it a shot. So let's see, here's Earth now. Yeah, all right, so this is Earth. And what I'm going to try to do is draw its axis, something like this. Maybe I'll move that over slightly. And so it'll come down through here as well. And so I assume that it's going to rotate around like this. And so by the right-hand rule, it would have an angular velocity that's pointing up its axis, the way that I've drawn it. So I could draw an angular velocity vector like this. Okay, so remember, omega has a direction given by the right-hand rule. I curl my fingers in the sense of the rotation of my right hand, and my thumb gives me the direction of that omega vector. Okay, fine. Then we've got this rotation axis that goes through the body of the Earth. And what I could imagine is dividing the Earth into these little point-like masses, little chunks of mass, and they're going to be some distance, say Ri. Let's see if I can make this look a little cleaner. So here's Ri. That's some distance from the rotation axis. So this is supposed to be a perpendicular distance. And so as the Earth rotates, this Ri spins around the rotation axis, and it has some angular momentum. So if this is mass mi, this is supposed to be vector ri. The I didn't really come out. There it is. Good. So the angular momentum of mi is, well, it's the exact same thing. It's mi times, let's see, it's going to be ri cross vi. So if this is rotating like this, it's like the mi is coming out towards us. So I don't know if I can draw it very well, but there would be like some velocity vi. It's kind of coming out of the page towards us. In fact, what I could do is for an object in circular motion, uniform circular motion at speed, angular speed omega, v is just equal to r times omega. Okay, so in fact, let's see, this is going to be, let's say, li. So that's going to be mi ri cross, well, it's omega cross ri. We could check that. We could do a right-hand rule. So omega cross ri. So I put my right arm in direction omega. I curl my fingers in that radial direction ri, and my thumb's kind of pointing out of the screen. So look, picture's not great, but that velocity is coming out of the screen. All right. But that's just for one of the point masses. I can imagine the Earth is made up of Avogadro's number of those little cubical masses, and I have to sum them all up to get the total spin angular momentum. So the total spin angular momentum is the sum of all mi's making up the Earth. Okay, and so we would say the spin angular momentum is the sum over I of mi ri cross omega cross ri, like so. In fact, because for our geometry, the omega and the ri are always perpendicular, you could just write that as omega ri. Okay. Oh, good. That's fine. This is more commonly expressed as I times omega, where this I is the rotational inertia. Okay, so that's the classical picture of spin. And so I'm not going to write anything else down, but let me just speak for a minute or 30 seconds or something like that. What we're going to find is that our electron also has a spin angular momentum. We're not going to derive it from any kind of first principle. It's an experimental fact. We'll talk about the experiment that shows the quantized spin angular momentum of the electron. You probably already know it from Physics 200. What is the experiment that shows that? Yeah, go ahead. Stern-Gerlach. So we'll talk about that a little bit later. So it's an experimental fact. The spin, although we have a classical picture of an orbiting sphere, for example, the electron, as far as we know, is like the structureless point particle, and it's represented by the smear of probability amplitude. So it doesn't make sense for us to literally think about a spinning electron because it has no shape or size. It's just a very good analogy with what we know about objects like Earth that are rotating about some other body, orbiting about some other body, and also rotating about its own axis. Okay, so we'll start working through the details of the electron spin on Wednesday. And this is going to be like talking about spin will be the last topic that we cover. All right. Thank you very much, everyone. Have a good evening, and we'll see you next time.